November 7th, 1944. 32,000 feet above Tokyo. Stakely adjusted his oxygen mask and watched ice crystals form on the inside of his bombardier's window aboard the B-29 reconnaissance aircraft. Call sign Tokyo rose. His hands, despite heated gloves, felt numb in the -60-degree air that seeped through every seal in the pressurized compartment. Below him, through breaks in the cloud cover, Tokyo sprawled across the Kanto plain like a detailed map came to life. This was the first American aircraft over the Japanese capital since Jimmy Doolittle's audacious raid 31 months earlier. But unlike Doolittle's low-altitude sprint in vulnerable B-25 Mitchells, Stakely's B-29 Superfortress cruised at an altitude where Japanese fighters gasped for air, and anti-aircraft shells burst uselessly thousands of feet below their target. The crew had been told this altitude would make them invincible. The engineering specifications promised it. The Boeing designers had calculated it. At 32,000 feet, Japanese interceptors would struggle to reach them, and even if they did, the thin air would rob enemy fighters of the performance needed to press effective attacks. The B-29 would revolutionize strategic bombing through sheer altitude advantage. 17 weeks later, on March 9th, 1945, Captain Stakely would return to Tokyo in a very different mission profile. His B-29 would cross the Japanese coast at 5,000 feet, low enough that anti-aircraft gunners could clearly see the bomber formations silhouetted against the night sky. Low enough that small arms fire from the ground posed a genuine threat. The aircraft would be stripped of most defensive armament to carry maximum bomb loads, abandoning the very protection system that had cost millions to develop. The journey from invincible high-altitude fortress to vulnerable low-altitude attacker represents one of the most dramatic, tactical reversals in aviation warfare history. It is a story about the gulf between engineering theory and combat reality, about jet streams that hadn't yet been discovered, about Japanese fighters that could barely function at designed altitude, and American bombers that dominated the stratosphere yet failed to achieve their primary mission. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Boeing B-29 Superfortress emerged from one of the most ambitious and expensive weapons development programs in American military history. In 1939, as war consumed Europe, United States Army Air Corps planners recognized that existing bomber designs, including the successful Boeing B-17 Flying Fortress, lacked the range and payload capacity needed for a potential war across the Pacific Ocean. The distances involved were staggering. From potential bases in the Mariana Islands to Tokyo measured approximately 1,500 nautical miles. A bomber would need to fly this distance, conduct operations over heavily defended targets, and return, all while carrying meaningful bomb loads and maintaining altitude high enough to avoid interception. Boeing received the contract to develop what they initially called a very long-range bomber. The specifications demanded performance that exceeded anything flying or under development anywhere in the world. The aircraft needed to carry a 20,000-pound bomb load over a combat radius of 1,600 miles, while cruising at speeds above 300 miles per hour, at altitudes exceeding 30,000 feet. These requirements drove revolutionary engineering solutions. Boeing designers, led by Chief Engineer Edward Curtis Wells, created an aircraft that was not merely larger than existing bombers, but fundamentally different in capability and complexity. The B-29 would feature a pressurized crew compartment, allowing men to work effectively at altitudes where unpressurized aircraft left crews gasping for oxygen and suffering from extreme cold. The pressurization system represented a massive technical challenge. The fuselage needed to maintain cabin pressure, equivalent to 8,000 feet altitude, while the aircraft operated at 32,000 feet or higher. This required a completely sealed crew compartment with airlocks connecting different sections. The forward pressurized section housed the pilots, flight engineer, navigator, bombardier, and radio operator. The rear pressurized section contained the gunners who would operate the defensive armament. The tail gunner occupied his own isolated pressurized station. But the most revolutionary aspect of the B-29's design was its defensive armament system. Boeing partnered with General Electric to develop a remote-controlled, computer-assisted fire control system unlike anything previously attempted in combat aircraft. The innovation would prove both brilliant in concept and problematic in execution. 5 gun turrets dotted the B-29's fuselage. 2 turrets, upper and lower, sat forward of the wing. 2 more, also upper and lower, were positioned aft near the tail. The tail itself mounted an additional turret with 2 50-caliber Browning machine guns and initially a 20mm cannon, though this cannon would later be removed due to ballistic trajectory mismatches with the machine guns. The revolutionary element was that gunners never touched the actual guns. Each turret was controlled remotely from one of 5 sighting stations distributed throughout the pressurized sections. A gunner would use an optical sight to track an attacking fighter, briefly holding the target in his crosshairs. During this tracking period, a General Electric analog computer analyzed the relative motion, calculated range and closure rate, and factored in airspeed, gravity, temperature, humidity, and the lead angle needed to put bullets on target. When the gunner squeezed his trigger, the computer directed the turret to aim not at where the enemy fighter was, but where it would be when the bullets arrived. The effective range of this computer-assisted system reached 900 yards, compared to perhaps 600 yards for manually aimed guns. In theory, a single B-29 gunner with computer assistance could outshoot multiple manual gunners in older aircraft. The system also allowed multiple gunners to control the same turret, or one gunner to operate multiple turrets simultaneously. The nose gunner could command both forward turrets together, creating a massive concentration of firepower against frontal attacks. The side gunners could control the tail turret if the tail gunner wasn't using it. The upper gunner, seated in what crews called the barber chair position, served as fire control coordinator, managing turret assignments during combat. This technological sophistication came with significant weight penalties. The 5 turrets, associated computers, electric motors, control systems, ammunition, and structural reinforcement required to mount them added thousands of pounds to the aircraft. But Air Force planners accepted this weight as necessary. The B-29 would operate at altitudes and distances where fighter escort was impossible. It would face interception alone, and it needed the firepower to defend itself. The engines driving this technological marvel represented another engineering frontier. 4 Wright R3350 duplex Cyclone engines, each producing 2,200 horsepower at takeoff, gave the B-29 performance exceeding any previous bomber. These were 18-cylinder radial engines, massive and complex, with 2 banks of 9 cylinders arranged in a radial pattern. Each engine featured exhaust-driven turbo superchargers that maintained manifold pressure at high altitudes. This was critical to the entire operational concept. Most piston engines lose power dramatically as altitude increases because air density decreases. At 30,000 feet, atmospheric pressure is only 1/3 of sea level pressure. An unsupercharged engine would struggle to produce even 50% of its rated power. The turbo supercharger solved this problem by using exhaust gases to spin a turbine that compressed incoming air before feeding it to the engine. This artificial boost maintained sea-level air density even at extreme altitudes, allowing the engines to develop nearly full power where enemy fighters suffocated. However, the R3350 engines proved temperamental in early production. Overheating plagued the design. Cylinders would crack, exhaust valves would fail, fuel injection systems would malfunction. In the rushed production schedule driven by wartime urgency, quality control suffered. Many early B-29 seconds had in-commission rates below 40%, meaning fewer than 4 out of every 10 aircraft were flyable on any given day. But when everything worked correctly, when engines ran smoothly and systems functioned as designed, the B-29 represented a quantum leap in aviation capability. Maximum speed reached 357 miles per hour at 25,000 feet. The service ceiling exceeded 31,800 feet. Combat radius with a full bomb load and maximum fuel approached 1,600 nautical miles. No other operational aircraft in any air force could match this combination of range, altitude, speed, and payload. The first production B-29 seconds began rolling off assembly lines in July of 1943 at Boeing's Wichita, Kansas facility. Additional production came from Boeing's Renton, Washington plant, Bell Aircraft's Marietta, Georgia factory, and Martin's Omaha, Nebraska facility. At peak production, the four plants together completed over 100 B-29 seconds per month. The strategic concept behind this massive investment was straightforward. B-29 seconds, based in the Mariana Islands, once captured, would conduct daylight precision bombing raids against Japanese industrial targets from altitudes between 25,000 and 32,000 feet. Japanese fighters would struggle to intercept at these altitudes, and those that did reach bombing altitude would face devastating defensive firepower from the computer-controlled turret systems. The cumulative effect of sustained high-altitude precision bombing would systematically destroy Japan's ability to manufacture weapons, build ships, refine fuel, and sustain its war effort. This was the same strategic concept that guided bombing operations against Germany, but executed with even greater technical sophistication. 21st Bomber Command, activated in early 1944, began operations from India and China in June of that year under Operation Matterhorn. The first combat mission targeted Bangkok on June 5, 1944. Of the 98 B-29 seconds that attempted takeoff from bases around Chengdu, China, 79 reached the target area. Results were poor. Bombs scattered across the city with minimal damage to the intended railway marshalling yards. The difficulties of operating from China quickly became apparent. Every gallon of fuel, every bomb, every spare part had to be flown over the Himalayan mountains from India, a route pilots called flying the hump. It took 7 transport flights carrying fuel to accumulate enough aviation gasoline for one B-29 combat mission. The logistics were unsustainable. The first mission against Japan proper from Chinese bases occurred on June 15, 1944, targeting the Imperial Iron and Steel Works at Yawata on Kyushu. 68 B-29 seconds reached the target area. Only 7 bombed the primary target. The rest scattered their bombs across the city or never located the target at all. Japanese fighters rose to intercept, but few reached the bomber's operating altitude. Anti-aircraft fire was moderate but mostly ineffective due to altitude. 1 B-29 was lost to combat damage. 4 more were lost to mechanical failures. The pattern established during these early missions would repeat through the remainder of 1944. B-29 seconds would fly at altitudes between 27,000 and 32,000 feet, well above the effective ceiling of most Japanese fighters. Interceptions occurred, but Japanese pilots found their aircraft struggling at these altitudes. Engines starved for oxygen, control surfaces responded sluggishly in thin air, climb rates dropped dramatically. The few Japanese fighters that managed sustained combat at 30,000 feet faced another challenge. The B-29's remote-controlled defensive armament proved surprisingly effective when it worked properly. Japanese pilots reported that American defensive fire seemed unusually accurate at long ranges. They were experiencing the advantage of computer-assisted gunnery, though they didn't understand the technology behind it. From the Japanese perspective, the B-29 represented a nearly impossible interception problem. Their best fighters, including the Kawanishi N, 1K Shiden and Nakajima Ki 84 Hayate, had service ceilings around 38,000 feet on paper, but achieving operational effectiveness at 30,000 feet proved far different from reaching that altitude in a brief climb. At 30,000 feet, these fighters had reduced engine power, mushy controls, degraded rate of climb, and limited maneuvering capability. A Ki 84 that could complete a sharp turn in 16 seconds at 15,000 feet might need 25 seconds or more at 30,000 feet. The pilot would be breathing through an oxygen mask, fighting hypoxia, struggling with a cold cockpit, and attempting to execute attack runs against targets defended by computer-controlled guns. American crews, meanwhile, operated in pressurized comfort at cabin altitudes equivalent to 8,000 feet. They wore heated flight suits, They could remove oxygen masks when not at their combat stations. The B-29's technological advantages extended far beyond simple performance specifications. Yet, despite these overwhelming technical advantages, despite operating at altitudes Japanese fighters could barely reach, despite defensive armament that outraged enemy guns, the high-altitude precision bombing campaign was failing to achieve its objectives. Mission reports from November and December of 1944 painted a frustrating picture. Bombing accuracy was abysmal. On the November 24th mission against Tokyo, the first large-scale attack on the Japanese capital from Saipan, only 24 of 88 aircraft that reached the target area bombed the primary target, the Musashino aircraft engine factory. The remaining aircraft bombed secondary targets, targets of opportunity, or simply dropped their bombs somewhere over Tokyo. Post-strike reconnaissance showed minimal damage to the intended target. Some bombs hit miles away from the aiming point. Others fell into Tokyo Bay. The cumulative tonnage dropped was impressive. The actual destruction of priority targets was negligible. The problem wasn't crew training, though many crews were still gaining experience. It wasn't courage, as crews regularly pressed through heavy anti-aircraft fire and fighter attacks. The problem was atmospheric conditions at 30,000 feet over Japan that nobody had anticipated and nobody yet understood. Strong winds at bombing altitude were carrying bombs far off target. The Norden bomb site, accurate when tested over the United States at more moderate altitudes, couldn't compensate for wind velocities exceeding 150 or even 200 miles per hour. Bombardiers would track their target visually, release their bombs at the calculated point, and watch helplessly as the wind stream carried their weapons miles downwind before impact. Weather added another complication. Cloud cover over Japan was dense and persistent during winter months. Visual bombing became impossible on many missions. Radar bombing techniques existed but were still primitive. The accuracy degraded further when bombardiers couldn't see their targets. The mechanical reliability problems that had plagued the B-29 during training continued during combat operations. Aircraft would abort missions due to engine failures, pressurization leaks, electrical system malfunctions, or turbo supercharger problems. On some missions, 30 to 40% of aircraft launching from bases would abort before reaching the target. Worse, when defensive systems failed at high altitude, they couldn't be repaired in flight. The remote-controlled turrets sat outside the pressurized crew compartments. If a turret jammed, if a computer failed, if an electrical connection broke, the crew couldn't reach the system to fix it. In older bombers like the B-17, gunners could sometimes clear jammed guns or perform field repairs during flight. In the B-29, a system failure meant a dead turret for the duration of the mission. Combat losses remained relatively low during the high-altitude campaign of late 1944. Japanese fighters accounted for some losses, anti-aircraft fire destroyed others, but mechanical failures claimed the most aircraft. Engines would fail over the target. Pilots would attempt to maintain altitude but gradually lose the battle against gravity. The aircraft would descend into denser air, where Japanese fighters could more effectively attack. Some crews made it back to friendly bases or ditched near rescue stations. Others disappeared over the Pacific. By early January of 1945, the strategic situation had reached a critical point. General Henry Hap Arnold, commanding the Army Air Forces from Washington, was receiving disturbing reports from the Marianas. Months of operations had consumed enormous resources, thousands of tons of bombs, hundreds of thousands of gallons of aviation fuel, and produced minimal damage to priority targets. The Industrial Analysis section estimated that the cumulative damage from all B-29 missions to date had reduced Japanese war production by perhaps 5%. At this rate, strategic bombing would never force Japanese surrender. The massive investment in the B-29 program, the most expensive weapons development project of the war, exceeded only by the Manhattan Project, risked becoming a strategic failure despite overwhelming technical superiority. Arnold needed results. He needed them quickly. The planned invasion of Japan, scheduled for November of 1945, depended on prior destruction of Japanese industrial capacity and collapse of civilian morale. If the B-29 seconds couldn't accomplish this mission from 30,000 feet, where they enjoyed near immunity from interception, Arnold would need to find commanders willing to try something different. On January 20th, 1945, Major General Curtis Emerson LeMay arrived on Guam to assume command of 21st Bomber Command. LeMay had built his reputation in Europe, commanding bomber units that systematically destroyed German industrial targets through relentless precision bombing. He believed in measurable results and had little patience for excuses. LeMay inherited 345 B-29 seconds distributed across bases on Saipan, Tinian, and Guam. He also inherited the accumulated frustration of 3 months of high-altitude missions that scattered bombs across Japanese cities without destroying priority targets. His initial reaction was to tighten formation discipline and improve bombing procedures. Better training would solve the accuracy problem. For 6 weeks, LeMay pushed his command hard. He flew on missions himself, observing problems firsthand. He watched bombardiers struggle with winds that seemed impossibly strong. He reviewed reconnaissance photographs showing bomb craters scattered randomly across landscapes, missing factories by hundreds or thousands of yards. He studied weather data and began to understand they were encountering atmospheric conditions far more severe than anything experienced over Europe. What neither LeMay nor anyone else in the Army Air Forces yet understood was that they had discovered the jet stream. These rivers of high-velocity wind flowing through the upper atmosphere at altitudes between 25,000 and 40,000 feet had been theorized by meteorologists, but never adequately studied or measured. The B-29 seconds, operating routinely at altitudes where jet streams were strongest, had become unwitting explorers of atmospheric phenomena that would only be properly understood years after the war. The jet stream over Japan during winter months reached velocities approaching and sometimes exceeding 200 miles per hour. Bombs dropped into this wind stream would be carried horizontally for miles before descending to target altitude. The Norden bombsite's mechanical computer couldn't account for such extreme conditions. Bombardiers found themselves dealing with ballistic problems that had no solution with existing technology. Temperature added another complication. At 32,000 feet over Japan during winter, outside air temperatures dropped to -60 degrees Fahrenheit or colder. Metal became brittle. Hydraulic fluid thickened. Electrical systems behaved erratically. Gun mechanisms froze. Oxygen regulators malfunctioned. The B-29's pressurization and heating systems maintained survivable conditions for crews, but just barely. Staff Sergeant Henry Red Irwin, a radio operator aboard a B-29 named City of Los Angeles, experienced the consequences of extreme altitude operations firsthand on April 12, 1945, during a mission against Koriyama. His aircraft was flying lead position at 27,000 feet when he received the order to drop a phosphorus smoke marker through a chute in the aircraft floor. These markers helped the following aircraft identify the lead bomber for formation assembly. Irwin pulled the pin and dropped the canister into the chute. The phosphorus ignited immediately as designed, but instead of falling clear of the aircraft, the canister jammed in the tube and bounced backward into the fuselage. White-hot phosphorus burned at 3,000 degrees Fahrenheit, melting through metal and filling the pressurized compartment with toxic smoke. The canister lodged against Irwin's chest, burning through his flight suit into his flesh. With visibility zero and the pilot unable to see instruments or windows, Irwin made a decision that would earn him the Medal of Honor. He grabbed the burning canister in his bare hands, burning away flesh to bone, stumbled through the smoke-filled cabin, navigated past the navigator's table, found the window, and threw the phosphorus marker out of the aircraft. The act saved his crew but left Irwin with catastrophic burns covering his face, arms, and torso. The incident illustrated the fine line between survival and catastrophe at extreme altitudes. A simple malfunction, the kind that might be manageable at lower altitudes, could turn instantly fatal when it compromised pressurization or created fire at 30,000 feet. Crews couldn't simply bail out through the nearest exit. They needed to descend to breathable altitudes first, find oxygen bottles, locate parachutes, and execute emergency procedures while dealing with whatever crisis had developed. The Japanese defenders, meanwhile, were learning to adapt to the high-altitude challenge. Their initial interception attempts in late 1944 had been largely ineffective, with fighters struggling to reach 30,000 feet and maintain combat effectiveness. But by early 1945, Japanese air defense units were developing specialized tactics. The Nakajima Ki-44 Shoki, codenamed Tojo by Allied intelligence, had been designed specifically as a high-altitude interceptor. Powered by a Nakajima Ha-109 engine producing 1,500 horsepower, the Ki-44 sacrificed the maneuverability and range that characterized earlier Japanese fighters in favor of speed and rate of climb. At 25,000 feet, a well-maintained Ki-44 could climb at approximately 2,600 feet per minute, faster than most Japanese fighters. Some Ki-44 units equipped their aircraft with 40mm Ho-301 cannon for attacking B-29 seconds. The massive shells, while slow-flying and inaccurate beyond 300 yards, could inflict catastrophic damage on bomber structures. A single 40mm hit could destroy an engine or sever a control cable. 2 or 3 hits could doom a bomber. Japanese pilots developed head-on attack tactics that maximized their brief window of interception opportunity. They would climb to slightly above B-29 formation altitude, position themselves several miles ahead of the approaching bombers, then dive toward the formation and execute a single high-speed firing pass. The closure rate during these head-on attacks exceeded 500 miles per hour, giving both sides only 2 or 3 seconds of firing opportunity. For the B-29 crews, head-on attacks proved the most difficult to defend against. The nose gunner would track the approaching fighter with his sight, attempting to hold the rapidly closing target long enough for the fire control computer to calculate a solution. But the extreme closure rate meant computers couldn't track effectively. Many times, the attacking fighter would flash past the formation before defensive guns achieved effective firing solutions. Japanese pilots executing these attacks faced their own challenges. At 30,000 feet, their aircraft handled sluggishly. The extreme cold numbed hands and feet, despite heated flight suits. Oxygen systems struggled to provide adequate breathing gas at maximum exertion. The thin air meant that slight control inputs could send the fighter into stalls or spins, and diving from above 30,000 feet at high speed risked compressibility problems, similar to those American P-47 pilots had mastered over Europe. Despite these difficulties, Japanese interception success rates improved during the early 1945. On February 19th, during a mission against Tokyo's port facilities, B-29 formations encountered sustained fighter attacks that destroyed 3 bombers and damaged 15 others severely enough to force them out of formation. Japanese pilots concentrated their attacks on aircraft that strayed from formation protection or showed damage from previous attacks. The defensive gun systems that had promised revolutionary firepower delivered mixed results in actual combat. When they worked correctly, they proved deadly. Multiple B-29 gunners reported successfully destroying Japanese fighters at ranges exceeding 700 yards, distances where manual gunnery would have been largely ineffective. The computer-assisted lead calculations proved accurate, and concentrated fire from multiple turrets could shred attacking fighters. But the system's complexity created reliability problems that had not been adequately addressed during development. Electrical connections would vibrate loose under combat stress. Computer vacuum tubes would fail. Mechanical linkages would jam. When a turret system failed, it typically failed completely, leaving that section of the aircraft undefended. Maintenance crews worked around the clock attempting to keep systems operational, but the in-commission rate for defensive armament remained frustratingly low. Worse, the automatic fire interrupter cams designed to prevent turrets from shooting friendly aircraft sometimes failed catastrophically. On several missions, B-29 seconds in tight formation accidentally fired on each other when turret control transferred between gunners and the guns swung through their own formation. 17 bombers suffered significant damage from friendly fire during bomb runs when automatic motion tracking systems mistook opening bomb bay doors for enemy movement and triggered turrets in nearby aircraft. These technical failures cost General Electric and Boeing credibility with combat crews. The gunners who had been promised revolutionary capability found themselves managing temperamental systems that required constant attention and frequently left them defenseless at critical moments. Some crews began requesting manual backup controls, only to be told that the aircraft's pressurization made this impossible. Once launched on a mission, they were committed to the remote control system, regardless of its reliability. Anti-aircraft fire, which planners had expected to be largely ineffective at 30,000 feet, proved more dangerous than anticipated. Japanese heavy anti-aircraft artillery, particularly the 120mm Type 99 gun, could reach 35,000 feet. While accuracy decreased significantly at extreme altitudes, volume of fire compensated. Over major targets like Tokyo, Osaka, and Nagoya, B-29 formations encountered barrages of heavy anti-aircraft fire that filled the sky with bursting shells. Each shell burst created a lethal zone approximately 50 yards in diameter, filled with steel fragments traveling at thousands of feet per second. The fragments could puncture fuel tanks, sever hydraulic lines, damage engines, or kill crew members even inside pressurized compartments. Aircraft flying in tight formation for mutual defensive fire support became easier targets for anti-aircraft gunners, who could aim at the center of the formation and achieve hits through volume rather than precision. Lieutenant Colonel Robert Morgan, who had piloted the famous B-17 Memphis Belle through 25 missions over Europe before transitioning to B-29 seconds in the Pacific, later wrote that anti-aircraft fire over Japan at high altitude was more intense than anything he experienced over Germany. The Japanese had learned to concentrate their heavy guns around critical industrial targets, creating defensive zones that B-29 seconds had to penetrate to reach their aiming points. The cumulative effect of these challenges meant that high-altitude precision bombing during January and February of 1945 continued to produce disappointing results. LeMay reviewed strike photos and damage assessments with growing frustration. The Musashino aircraft engine plant, attacked repeatedly as a priority target, showed minimal cumulative damage. The Mitsubishi aircraft factory in Nagoya had been hit multiple times but continued operating. Oil refineries, steel mills, and chemical plants that were supposed to be destroyed remained largely functional. Arnold sent increasingly pointed messages from Washington demanding better results. The strategic bombing campaign was consuming enormous resources. Each mission burned thousands of gallons of high-octane aviation fuel that had to be transported across the Pacific. Every bomb dropped represented industrial capacity and raw materials that could have been used elsewhere. The airfields on Saipan, Tinian, and Guam required constant supply by cargo ship. Crews needed food, ammunition, spare parts, and endless maintenance support. If the B-29 offensive couldn't destroy Japanese industrial capacity more effectively, questions would arise about whether the resources should be diverted to direct support of the planned invasion. Arnold made it clear to LeMay that 20th Air Force needed to justify its existence through measurable destruction of Japanese targets. LeMay began examining alternatives. High-altitude precision bombing had been the established doctrine, proven over Europe against Germany. But Germany didn't have jet streams. Germany had different weather patterns, and German industrial targets were often large, concentrated facilities that could absorb significant targeting error and still be hit. Japanese industry was more dispersed, with small workshops and cottage factories scattered throughout urban areas feeding parts to larger assembly plants. Intelligence reports provided another piece of the puzzle. Japanese cities were built primarily from wood and paper. Unlike European cities with stone and concrete construction, Japanese urban areas were essentially tinder waiting for ignition. An incendiary attack might prove far more effective than high-explosive bombs, especially if the goal was to destroy the dispersed light industry supporting Japan's war production. Army Air Force analysts had studied this possibility. In 1943, they constructed a replica Japanese village at Dugway Proving Ground in Utah, complete with authentic building materials, room layouts, and furnishings. They then tested various incendiary bomb types against these structures. The results were dramatic. Properly designed incendiary weapons could create uncontrollable fires in Japanese urban construction. The most effective incendiary proved to be the M69 oil bomb, a 6-pound hexagonal cluster munition filled with napalm. Each cluster contained 47 individual bomblets that would separate after release and scatter across a wide area. Upon impact, the napalm would ignite and burn at temperatures exceeding 2,000 degrees Fahrenheit, hot enough to ignite wood, paper, and fabric instantaneously. A single 500-pound cluster of M69 incendiaries would scatter 110 individual fire-starting bomblets across an area roughly 200 by 50 feet. A B-29 carrying a maximum incendiary load could deliver 40 clusters, potentially starting 4,400 individual fires across a target area. A formation of 300 B-29 seconds could theoretically ignite over 1 million individual fires simultaneously. But using incendiary weapons required different tactics than high-explosive precision bombing. Incendiaries worked best when dropped from lower altitudes where accuracy improved and wind effects decreased. They were most effective at night when firefighting services had difficulty responding and when thermal updrafts from growing fires would spread combustion to persist. Adjacent structures. Lower altitudes meant B-29 seconds would be within range of Japanese fighters operating at their optimal performance altitudes. It meant exposure to more accurate anti-aircraft fire. It meant abandoning the altitude advantage that had been the cornerstone of B-29 operational doctrine. Every instinct LeMay had developed through years of high-altitude daylight bombing over Europe argued against low-altitude night operations. Yet the high-altitude campaign was failing. Something needed to change. On February 25, 1945, LeMay authorized a test mission against Tokyo using incendiary weapons from high altitude. 172 B-29 seconds would attack at 25,000 feet, dropping M69 incendiary clusters on residential and light industrial areas. The goal was to assess whether incendiaries could succeed where high-explosive bombs had failed. The mission burned approximately 1 square mile of Tokyo, destroying around 28,000 buildings. Strike photographs showed devastation far exceeding any previous raid. Intelligence estimated that hundreds of small workshops and cottage factories had been eliminated. The thermal destruction was comprehensive within the impact area, leaving only ashes and twisted metal. But the mission also revealed problems. At 25,000 feet, bombers still encountered strong winds that scattered bomblets across wide areas, diluting the concentration needed for firestorm development. Fighter attacks, while not severe, demonstrated that Japanese interceptors were becoming more aggressive and effective. Anti-aircraft fire damaged several aircraft seriously. LeMay studied the results and made a decision that would prove to be the most controversial of his career. If incendiaries were effective, he would use incendiaries. If altitude caused accuracy problems, he would attack from low altitude. If daylight exposed his bombers to fighters, he would attack at night. And if the defensive armament added weight without providing proportional protection, he would strip most of it out and carry more bombs instead. The decision represented a complete reversal of established bombing doctrine. Every principle that had governed strategic bombing operations for years would be violated. The B-29 had been designed specifically for high-altitude operations. Its pressurization, its turbo-supercharged engines, its remote-controlled defensive systems, all optimized for combat at 30,000 feet. LeMay was proposing to throw away these advantages and fight at altitudes where Japanese fighters performed best. His staff objected strenuously. Flight leaders argued that low-altitude night missions would result in catastrophic casualties. Intelligence officers predicted Japanese fighters would devastate formations operating at 5,000 feet. Maintenance officers worried that removing defensive armament would create unacceptable vulnerability. LeMay listened to the objections, then issued the orders anyway. The mission would launch on the night of March 9th, targeting Tokyo. 334 B-29 seconds would attack from altitudes between 5,000 and 7,000 feet. All defensive armament except tail guns would be removed to maximize bomb loads. Each aircraft would carry between 6 and 8 tons of M69 incendiary clusters. The mission would begin shortly after midnight and continue for approximately 3 hours, allowing fires from early arrivals to guide later waves to the target. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Crews received the briefing on March 8th with reactions ranging from shock to outrage. Pilots who had spent months perfecting high-altitude formation flying were being told to attack individually at 5,000 feet, low enough for small arms fire from the ground to damage their aircraft. Gunners who had trained on the sophisticated remote control system were told most of their turrets would be physically removed, leaving only the tail position operational. Technical Sergeant Henry Hank Leffler, a right gunner aboard a B-29 named Goin Jesse, later recalled the briefing. "We thought LeMay had lost his mind. Everything we'd been taught said altitude was life. Now we were going down to 5,000 feet over the most heavily defended city in Japan. At night, with most of our guns removed. Some guys were writing letters home before the mission like they were saying goodbye." Aircraft commanders protested directly to LeMay during mission planning sessions. Removing defensive armament seemed suicidal. Flying at 5,000 feet put them within effective range of every anti-aircraft gun in the Japanese inventory, from heavy artillery down to automatic cannons and machine guns. Night operations meant no possibility of mutual defensive fire support from other bombers in defense formation. LeMay's response was characteristically blunt. The high-altitude campaign had failed to produce significant damage. Japanese industry continued functioning despite months of bombing. If the B-29 force couldn't destroy Japanese industrial capacity, it had no purpose. The mission would proceed as ordered. What LeMay understood, and what many of his subordinates did not yet grasp, was that the strategic situation demanded results that high-altitude bombing could not deliver. The planned invasion of Japan, Operation Downfall, was scheduled for November 1st, 1945. Casualty estimates ranged from hundreds of thousands to over 1 million American servicemen killed or wounded. The only way to avoid or minimize this bloodbath was to force Japanese surrender through strategic bombing and naval blockade before the invasion began. High-altitude precision bombing had not broken German will to resist and had required years of sustained operations to achieve industrial damage. Japan had fewer years. The war needed to end in 1945, which meant bombing needed to produce rapid, visible, undeniable destruction of Japan's capacity to continue fighting. LeMay had seen the test results from Dugway. He understood that Japanese urban construction was fundamentally vulnerable to fire. He recognized that destroying the dispersed cottage industry, supporting Japanese war production, required area attacks rather than precision strikes. And he calculated that his crews, despite their fears, would survive low-altitude missions because Japanese night fighters lacked the radar-equipped capability to find and track individual bombers in darkness. The removal of most defensive armament represented a calculated trade-off. Each turret, computer, and ammunition load removed freed up between 2,500 and 3,000 pounds of payload capacity. This weight could be converted directly into additional bombs. A B-29 that normally carried 6 tons of ordnance could carry 8 or even 9 tons when stripped of excess defensive systems. Moreover, the defensive systems had proven less effective in combat than designed. The complexity created reliability problems. The automatic fire control sometimes malfunctioned dangerously. Keeping all systems operational required maintenance hours that were in short supply. And at 5,000 feet in darkness, with aircraft operating individually rather than in formation, the defensive guns would have limited utility anyway. Japanese fighters would have difficulty finding targets, and those that did would likely attack from positions where single-tail guns provided adequate defensive coverage. The night of March 9, 1945 began with organized chaos on airfields across the Marianas. Crews walked out to their aircraft under lights that turned the massive bombers into surreal shadows against tropical darkness. Ground crews worked final checks, loading the last incendiary clusters and topping off fuel, tanks. The smell of aviation gasoline hung thick in the humid air. Pilots conducted their pre-flight checks and discovered aircraft that felt strange without the familiar weight of forward defensive turrets. The nose seemed lighter. The aircraft's center of gravity had shifted slightly aft. Flying characteristics would be subtly different, though not dangerously so. Engineers had calculated the changes and confirmed the modified aircraft remained within acceptable handling limits. At 1,736 hours, the first B-29 lifted off from North Field on Guam. Every 90 seconds, another bomber followed, climbing into darkness and turning northwest toward Japan, 1,500 miles distant. Aircraft from Tinian and Saipan launched simultaneously, creating a stream of bombers that would converge on Tokyo from slightly different approach angles. The flight required approximately 6 hours. Crews settled into the routine of long-distance navigation, monitoring engines, adjusting fuel mixture, and tracking position. Radio silence was strictly maintained to avoid alerting Japanese defenses. Each aircraft flew independently, following identical routing but spaced to avoid collision in darkness. Weather over the Pacific was generally clear with scattered clouds. The moon, in the first quarter, provided enough illumination for crews to maintain visual reference to the horizon, but not enough to create serious visibility for Japanese defenses. Wind conditions at cruise altitude were moderate, not the extreme jet stream velocities encountered at 30,000 feet. As B-29 seconds approached the Japanese coast, crews began final preparations. Bombardiers armed their weapons. Gunners checked tail turrets and prepared ammunition. Pilots descended to attack altitude, leveling off between 5,000 and 7,000 feet. The decreased altitude after hours at higher cruise altitudes meant cabin pressure had to be carefully managed to avoid crew discomfort from rapid pressure changes. The first aircraft over Tokyo, Pathfinders carrying a higher proportion of high-explosive bombs along with incendiaries, arrived shortly after midnight. Their targets were specific areas of the Shitamachi district, a densely populated residential and light industrial area covering approximately 12 square miles, with an estimated population exceeding 300,000 civilians. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.